Thank you. So, thank you all, and thanks to the Hypersite for inviting me. Um, like he said, all the way from Cupertino, California. So, we get started with Silicon Valley. How many of you have been to Silicon Valley? Oh, that's more than 40%. That's great. So again, thank you for inviting me. I'm Bhairav Mehta. This is my background. I'm an academician and a veteran at Apple for the last 10 years. I've seen it all, the whole iPhone journey as we go from iPhone 3G to today. So you see that digital economy migration that has happened in the last 50 years. Right now, the digital economy controls more than, I would say, around $3 trillion and around 15 to 20% of US GDP. So you can imagine the amount of data that's being created and also the challenges we have today with respect to privacy and GDPR and all the other challenges we have with the data governance. So currently, we have something called Unicorn Club in Silicon Valley and rest of the world. These are the companies with more than $1 billion valuation. So you see that when the floodgates open, like around 2014, we started seeing a lot of companies grow to more than $1 billion valuation. And what was responsible for this? So most of the responsibility goes to like mobility, the mature mobile. 4G was released around this time. The cloud maturity that really reduced the product life cycle. And also what you see is, in general, the algorithmic and data explosion that we see today. All of these are responsible for these unicorns. And many of them are part of your cell phone icons that you download the apps and so on. So we'll be talking more about that. Right? So we are in a digital correlation today. This digital correlation is for cloud computing, artificial intelligence, Internet of Things, fog or mist computing, and data analytics. These are the 5 technologies that are driving our industry today, especially the data economy that we live in. And all of this can sit in a blockchain. So I was talking to the chair of the Hypersite conference, this data innovation conference, and he was talking about distributed ledger, and he was talking about the double spending problem and so on, and smart contracts. And all of these technologies will enable that type of future, and we'll be talking more about that later on. So if you see the hype cycle today, the deep learning is a peak of inflated expectation. That's where we are at right now. In 2018, Gartner hype cycle says deep learning is a peak of inflated expectation. There's a lot of expectation around this technology, and that will be focus of our talk. Okay? So there has been a chip to AI transition in last year or so, maybe 2 years, I would say. No chip company wants to call themselves a chip company anymore. Everybody wants to call themselves a platform company, like Qualcomm wants to call themselves platform company, or Intel wants to call itself a data company. NVIDIA calls itself amplifying human intelligence. So all of these, as you see the transition all the way from if you look at the performance and functionality versus inference and training, you see all of these technologies have matured over time. We have Altera FPGAs, Google TPUs, the NVIDIA's platforms that we have for training and inference. Okay? There are 5 tribes of machine learning in the industry today. 5 tribes. So if I go back to my graduate school, we had symbolists, right? More of them are rules and decision trees. Then came Bayesians. Bayesians were more on a population, more probabilistic models, versus connectionist, that we are going to talk about today, is about neural networks. You recognize and generalize patterns dynamically with matrices of probabilistic weighted neurons. Then we have evolutionaries and analogizers. So evolutionaries are more like generative models, generative adversarial models. And we have analogizers, which are more like reinforcement learning models where you're trying to optimize a function in light of constraints. So you have these 5 tribes of machine learning algorithms. And there are rules and decision trees, naive Bayes or Markov chains, neural networks, the genetic programs or the generative models, or support vectors or reinforcement models. So how is the training or how the machine learning modeling process works, right? So we have had many talks in last few days, yesterday and today, and essentially in a supervised learning algorithm, what we are looking at is we have raw data, we have labels, label data, right? And yesterday there was a talk that label data is the biggest asset you can have, and the importance of data in general, what we are talking about here. And what we have, we do feature extraction or feature engineering, okay? And then we train the model, and then we build the model, we evaluate the model, and then that's an iterative process. And then you deploy the model, the pre-trained model, with the new production data, and then you get the labels as an output of that, okay? So these are some popular machine learning models and how the solution space look like. On the left-hand side, we have all of these different classification problems. There are classification problems where we are looking at partition lines or maybe a circular pattern or more chaotic patterns, and how these models are able to solve the problem. So we have nearest neighbor. In the first case, we have support vector machines, and nearest neighbor give you high accuracy versus the second model, the nearest neighbor gives you better accuracy, versus the last one, we have a whole slew of classification models like random forest and others gives a better model for accuracy. So let's talk about neurons. So going back to 1899, Santiago Ramon took out the fruit fly neurons. These are fruit fly neurons that are shown here on the left and left-hand side. And what we are looking at here is how the neurons are modeled, right? So it's a basic linear algebra. You have inputs x0 to xn. You have weights. That's essentially a slope of the line that's being fit. You have the bias. You're trying to fit a line. You always have an intercept. That's a bias. And then you put it through an activation function to get the threshold. When the values reach the threshold, it gets activated, or a synapse, as we call it, right? So that's the neuron modeling. This is the history of AI in the last few years, from 1958 to today. We have a few scientists we want to credit the AI revolution for. Dr. LeCun, who's at Facebook from NYU. We have Dr. Vapnik from Columbia. We have Dr. Hinton from University of Toronto. He's at Google. Dr. Bengio from University of Montreal, who is at Microsoft, and Dr. Goodfellow from Stanford. He also works at Google. And these are the individuals. Dr. LeCun is credited for all of the convolution neural network that we're going to talk about. Dr. Hinton is for the restricted Boltzmann machine and the backpropagation methods, and Dr. Bengio for stacked autoencoders. So all of these techniques are at the forefront of all the innovation that's happening in the industry today. So if you look at the propagation of computer vision, so what you have on the x-axis are all the different ImageNet models, the ImageNet competition that happens annually. That's the starting from 2010 to 2017. These are the models that win the competition. We have NEC, UIUC, XRCE, AlexNet, ZFNet, GoogleNet, ResNet, and SCNet. GoogleNet and ResNet is from Microsoft, and SCNet is a squeeze excitation network, which is a combination of the GoogleNet and ResNet, okay, that win the 2017 competition. So as you see, the computer vision problem has been more or less solved because we have bypassed the human performance zone. The human performance zone is around 5 to 10% error rate. we are at around 2 to 3% error rate. So you are seeing the computer vision problem has been solved. And same thing you can see for speech and text recognition or classification. We are at less than 2% error rate in most of these problems. And that's why you are able to see all of the advanced unstructured data problems that are already getting solved with robotics and other computer vision solutions. So if you look at our senses, especially the vision, we look at around 4 terabytes of content every second, and how much of that information can be programmed or can be trained through neural network. So what we are looking at on the left-hand side is a classic convolution neural network, where we are looking at like a photograph, and we are trying to identify if it's a car or person or an animal. And it goes through the standard set of layers. The first layer is usually the hidden layer that gets the edges and then the corners and contours. The second hidden layer, and then you have a third hidden layer, which is gets the object parts. And then it classifies it among the 3 categories that we have: a car or a person or an animal. In this case, the person. Okay, so that's the convolution neural network. And what we are looking at here is all the models that we saw in the previous slide in the human vision zone. These are the pre-trained models, and the accuracy we have received with these models. And these are the standard layers that it goes through to rectify linear unit or a convolution, and then pooling layers and other set of layers, or filtering through the content of the image, and it gets to the final object detection. Okay, so that's the ImageNet networks and accuracy of them. And what we are looking at here is the region proposal-based convolution neural network, where we are able to segment objects using region proposal. So what does region proposal means is essentially, so the previous problem I just explained with the photo of the women, we are trying to go through the layers and try to identify the person or a car or animal. In this case, what we are trying to do, we are just not trying to identify or classify the object, but there are multiple objects in an image, and we are trying to segment them and then identify them, right? In that process, you need some region proposal. So region proposal are essentially lookup tables or some proposal that you give it to the model that, okay, these are the objects I'm looking for in this image, and please identify them. And then we call it region proposal network, RPN. And then we also give it a mask. So masks are essentially the object boundaries that can be inputted to the network. If we input these 2 items to the network, you are able to segment the images into disparate objects and identify them in the same image, right? So this is a use case of a self-driving car, or you're trying to identify objects through a smart camera and so on. And then there are many different RCNN models, a fast RCNN or a faster RCNN or a mask RCNN. These are the different models available today. Then we get into the text analytics side. Okay, text analytics side, it's going through a lot of evolution in last few months. We are seeing that the standard natural language processing, that a part of speech tagging or syntactic parsing or named entity recognition or co-reference resolution, semantic parts and relation extraction or dialogue agents. These are some standard natural language processing or natural language understanding models that are out there, and they have been around for a while. But how do we take these very mature techniques in NLP and apply it to deep learning? In that, we need to create word embedding, word vectors, and word embedding layers. And now, similar to the previous model that you looked at, the pre-trained models like the VGGs, the ResNet, or GoogleNet, you also have similar models in text classification. Those are pre-trained models that can be used to identify or do some unsupervised text classification. So on the right-hand side, what I'm showing here is is the unsupervised pre-trained models here. Through the unsupervised learning, what you're seeing how the text can be classified and clustered together in general, and how the tone of a text based on the sentiments can be color-coded at the same time. And those are the exercises we can talk more about in the next slide. So what I'm showing here is a multi-dimensional text input, and I'm trying to identify a sentiment for that particular text blob. I can create word vectors out of it, and out of word vectors I can do word embedding. And from word embedding, I can identify and infer and input the numbers that are generated through word embedding. There are pre-trained models like GenSim, or there are other models like word-to-vector models or GLOVE models. We can create embedding numbers, and then I can input those numbers through the neural network, similar to the way I input pixels of the images, and I'm able to train a sentiment engine. Okay, so the concept of pre-trained and transfer learning, where we have state-of-the-art pre-trained models like the VGGs or ResNet or GoogleNet, or in this case of text processing, it's Elmo or ULM Fit, or we have BERT. There are other pre-trained text embedding models that can be used for, those are pre-trained models that can be used, and the transfer learning can be done to reduce the training time. So there are 3 strategies for transfer learning. You can do train the entire model, right? That will be too much time. Or train some layers and leave the others frozen. Or I can freeze the convolution base and just do the predictions, right? So all of these are different strategies for a pre-trained or transfer learning. Okay, so we learned how to build models, right? In one of the slides, I showed you the training procedure, the training process that we entail usually. But all the entities we have in that particular supervised learning and training models is training data. We have exported models. We have pre-processed data. We have test data. We have evaluation matrix. We have all the other models and metadata that's generated through the training process. There needs to be some kind of orchestration of that, right? Currently, if we don't have orchestration, then it becomes very, very difficult to deploy the model on different media that are different platforms that we want to deploy these models on, because nowadays everything is on the cloud and the training has to be done also on the cloud. So Kubernetes and Kubeflow and Seldon, Pachyderm, these are the tools that are available for you to first start orchestrating containers, then create CRDs, packaging, and notebooks, and then we can serve the models. We can do version control on it. We can create pipelines through various different tools that are available in the orchestration model. So that brings us the case of the federated learning model. Okay, the federated learning model is all about how we can use the existing phones, because most of the phones nowadays are very equipped with AI chips. They have high memory. The common phones have few gigabytes of memory. More expensive phones nowadays have even terabyte SSDs in them. And there are around 2.3 billion flagship phones out there. These are underutilized processing capacity. What if we can use those phones to train the models instead of, or each phone has its own experience because everybody uses the phone differently. How about we enrich the models based on the usage of the customers, and these models send out their candidate models to the cloud, and we can create a federated learning model where you can have customized experience on every phone. In this case, you can have essentially each phone send out its model and then improve the training process. So you essentially you do learning on the phone, you upload the summary, you update the consensus, you download the model on the phone, and that cycle keeps on going, right? So that's a federated learning model. So what I try to do in this very short time we have, and we are almost out of time, is to try to understand all the different aspects of neural networks and deep learning and training processes and the complexities that are involved in that. So I try to cover that in the 20 minutes time we had.
Thanks a lot, Bhairav. Very, very impressive.